Hello, we're taking our first look at Unit 2 notes. We're going to start right here on page 1, our very first problem, where we're looking at a transportation connection. Please read this problem. I'll read it with you this first time. As we're reading, we're simply looking for some important information that we might use as we work with our problem. Jacksonville, Florida has an elevation 12 feet above sea level. A hot air balloon, taking off from Jackson, rises 50 feet per minute. Write an equation to model the balloon's elevation as a function of time. Elevation as a function of time. Graph the equation. Interpret the intercept at which the graph intersects the vertical axis. I see a couple things that we're going to use here. First of all, I'm going to circle my numerical information in purple. Second, I'm going to be looking in the things in green that are going to tell us what we know and what we're looking for. Since I'm looking for elevation as a function of time, what that means is the elevation changes based on time. Time happens first. This is going to be our independent. Our independent variable is what changes, and the elevation is the result. That makes it our dependent. This is helpful to know. If I know that time is my independent, I know I'm going to be graphing and writing an equation and then interpreting. That independent variable, remember, that's what can stand on its own, and when you stand on your own, you stand on the ground. That means I'm going to graph time on the ground part of my graph. Now, I don't quite know what kind of scale I should be using yet, so I'm going to leave that part blank. What's going to depend on time, how much time I give this balloon to start rising or falling, is going to be the elevation. That means that's going to go up on my y-axis, my vertical. That's what changes as a result of my independent variable. Now that I have some information and I have a good start where I can begin plugging some items in, I'm going to think about the numerical information it gives me. First of all, it starts at 12 feet above sea level, and it's rising. When we're writing a linear equation to model a situation, sometimes it's helpful to begin with where we're going to start, and then add or subtract how it changes. This how it changes is also known as the rate. This rate tells me how quickly something changes. This balloon happens to start at 12 feet above sea level, and its elevation, I'm going to call that elevation E. Elevation is where it starts. It starts at 12. It is rising, so I'm going to add to this elevation. And I'm going to add 50 feet per minute that I give it to rise. 50 feet for every minute. So I'm going to say 50 times t. So what I'm looking for is time down here. I'm looking at in minutes. This tells me that the balloon starts at 12 feet, rises 50 feet every minute I let it rise. I've written our equation based on what it starts with and how its rate changes. Now I'm ready to create this graph so I can get a visual of what this looks like. This is a great time to pause right now and see if you can set your graph in motion. Set a scale across the bottom and upwards. and graph some key points on yours. Please pause the video, answer the question, and return.